Okay, so good afternoon, everyone. We are Group 1, composed of Anthony Bilic, Kunyang Lee, David Shotwell, Zain Olabedin, Farhad, and Kevin Tsai. And today we have the opportunity to present a paper titled FILIP, Fine-Grained Interactive Language Image Retraining by Yao and others, which was presented as a poster on iClear 2022. Okay, so as a brief outline, we will start with the background and the motivation behind the work, then go through the methods and what ideas are new to FILIP, then go through the results, conclusions, and limitations. So what is the problem? So FILIP is, as you all know, a vision language model, which tries to match the visual and the image and text features using constant similarity and contrastive learning. However, it is not able to capture fine-grained interactions between the objects in the image and the words in the text. And this happens because it uses global features, which capture the global information of the images and the sentences. So as I mentioned, this cannot capture relationship between individual image patches and textual words. Another problem of FILIP is that it struggles on very fine-grained image classification tasks, such as, for example, telling the difference between car models and variants of aircrafts. And this is actually a problem that OpenAI points out. So there are two main branches of work that try to solve this problem of learning fine-grained interactions. The first one are attention-based models, in which we have an image which goes into an image encoder, which is often a vision transformer. And then we have a text, which goes into a transformer. And both the image tokens and the text tokens are fused together with an attention mechanism. Some examples of these are Albev and Build. Then we have region of interest-based methods in which an image goes to an object detector, which basically finds all the objects in an image. For example, here's a patch with an image of a dog, and then here's the couch. And then we extract some features from those regions of interest, as we also extract some features from the text, and then they are fused together using a transformer. So the problem with these approaches is that, number one, attention is a costly operation because it scales quadratically with the size of the input tokens. And also, in the case of region of interest-based approaches, the performance of downstream tasks depends on the performance of the object detector. And a third drawback of these methods is that both are based on single-stream models, which means that during inference, it's not possible to pre-compute the image or text tokens. So during inference, it's actually slower. Well, some examples of region of interest-based models are Visual BERT and Uniter. So what are FILIP's main contributions? First of all, it overcomes the previous issues by using token-wise similarity between the image patches and words in text. It also uses prompt templates for downstream tasks, which are able to provide more robust classification. It also introduces several optimizations to reduce the training time. And finally, it demonstrates improved zero-shot classification and image-to-text retrieval over clip. Okay, so now let's look at the method. And first, let's start with the overall architecture. In general, the architecture of FILIP is very similar to the architecture of CLIP. So we have an input image, in this case of a cat, and an input text, which is a sentence saying a cat in the basin, for example, with a begin of sentence and end of sentence tokens. The image is divided into several patches, which are linearly projected and then concatenated with positional embeddings. And here we also have a CLS token. All of these image tokens go through an image encoder, which is usually based on the vision transformer. And then for the text, they are transformed into text tokens, also concatenated with positional embeddings. And they go to a text encoder based usually on the transformer architecture. Now, in CLIP, FILIP only extracts one image token and one text token from the whole image and the whole text. In this case, they use the CLS token as the final representation of the image, and the end of sentence token as the final representation of the sentence. But if, in contrast, FILIP uses all of the tokens related to all of the image patches, as well as all of the words in the text. So before this, they linearly project it into a shared feature space, and then use L2 normalization. So after this step, they use an algorithm called cross-modal length interaction, which basically computes a token-wise similarity matrix between each of the image and text tokens. And lastly, they reduce this token-wise similarity matrix by using the maximum and minimum operation across the rows and columns of the token-wise similarity matrix in different orders, basically to produce one single score for image to text similarity and one single score for text to image similarity. And then they repeat this procedure for every image text pair in the batch. So now let's take a look, a more closer look to how the cross-modal interaction mechanism actually works. Okay, so assume that we have a batch of images and text, and we sample one image I and one text J. The image and the text go through their respective encoders, which produce a set of N1 image tokens and N2 text tokens. In this case, N1 is a fixed number because the images are resized and they always have the same number of patches, but N2 can actually be variable and depends on the length of the sentence. So the next step is to take the cosine similarity between pair of image and text tokens, which produces a token-wise similarity matrix. Now, as I mentioned earlier, we want to reduce this similarity matrix to a couple of scores, right? So if we start with the image to text score, the first step is to find which of the text tokens have the highest similarity to each of the image patches. And mathematically, this is done by computing the maximum across the across the columns of the token-wise similarity matrix. And the result will be a column vector of size N1, which is the number of image patches. And then this column vector is then further reduced by taking the average across all of its elements. So the result will be a single score, which corresponds to a single entry in the image to text similarity matrix for the whole batch of image text pairs. Now, for text to images, the procedure is actually very similar, but instead of taking, in this case, the maximum value across the columns, we now take the maximum value across the rows. So the result is a row vector of size N2, which is further reduced by taking the average across all of its elements. And the resulting number is an entry in the text to image similarity matrix for the whole batch. Okay, and finally, after computing the similarity between all images and all text, we now want to compute the final step, which is the contrastive loss. So here we have the image to text similarity matrix for the whole batch. And for this, we have to apply the log softmax operation to each of the rows, which gives a result. The result of this operation is basically a loss for each of the images in the batch. And then by averaging all of the values, we get the overall image contrastive loss. For the text to image similarity is very similar. Again, we apply the log softmax operation to all of the rows. We have one loss for each text. And then the overall text contrastive loss is just the mean of all the values. And the final loss for the batch is just the average between the image contrastive loss and the text contrastive loss.
So the data set that FILIP uses is comprised of 4 different parts. So they came up with their own data set called FILIP 300M, consisting of 300 million image text pairs, covering a broad range of vision concepts. This one is open source, CC3M. They took 3 million from here. CC12M, they took about 10 million from here. And YFCC 100M, and they took about 26 million of the 100 million total from this data set. And these three here are open source. They combine these and apply some image text filters to get more quality data. Specifically for the images, they take only the images for which the height and the width, the minimum is greater than 200 pixels. You don't want it to be too small, and the aspect ratio must be less than 3. You don't want it to be too wide. And for the text, the sentences must be English. They must be meaningful, so you can't have something that's like image 0, for instance. And text must be repeated less than 10 times. And afterwards, you come up with about 340 million pairs, and they call this FILIP 340M. And so for some of the image text pairs, they apply data augmentation. For images, they use this method called auto augment. They use this technique called auto augment, and they apply some transformations such as equalize, rotate, solarize, and you can see some of the effects here on this building of church. And for text, they use this concept called back translation. So for instance, the original text reads, "This is a photo of a nice house." They translate that to Russian. In other cases, they translate that to German, and I can't pronounce this, but they back translate this back to English, and this is a photo of a beautiful house. So you can see that these two are synonyms, and so we get a more diverse range of image text pairs. To further augment the data, especially for downstream and inference, the authors came up with what's called a prompt ensemble. So these are basically templates following this pattern. You have a prefix, a label. Now this is the data set label, category description, and suffix. And so I'll run through an example real quick. For example, Stanford car. This is a data set with a variety of different car models from different years. And if we take one from each of these, for example, a photo of a type of car and is important to me, we come up with this sentence. A photo of an Audi 100 sedan 1994, a type of car, is important to me. And they also do this for CFAR10 and some other data sets. So what happens during FILIP inference? So you take an image. This is an image of a building. You have building as label. This label is passed through the prompt ensemble. So you have a number of different prompts. Photo of a building is common daily life. JPEG of a building, I like it. And you compute the similarity between the image I and each of these prompts. And then you take the average of those. C is number of prompt templates. So you have C of these. And you get the similarity of this image with this label. So then the experimental setup, what exactly is their architecture, their plane dimension, the details of their image encoder, text encoder, etc. So they have two different models they came up with. They have their base model and their large model. Now, FILIP base uses a bit base 32 backbone, and they train that for 9 days on 128 NVIDIA V100s. And for their larger model, they use a bit large 14, trained for 24 days, and on 192 NVIDIA V100 GPUs. And as you'll notice, the input resolution of the images is 224 by 224, divisible by both 32 and 14. And they cap the maximum number of text tokens. So this is the number of tokens you have in your supposed sentence at 77. Your vocabulary size is about 49,000. They use the LAM optimizer and a cosine learning rate schedule plus a linear warm-up. So they start with a base learning rate and they go into some final value. Also have weight decay, so the weights don't get too large. This is good for train stability. And so you have some additional statistics here. FILIP base, as you can see, they trained also on YFCC 100 million, and this is for their ablations. Philip Large is just trained on Philip 340M. So they want to make it efficient. Why? Because Philip, unlike CLIP, determines similarity between the tokens, not just the images and the text holds. So they reduced embedding size from 512, which is in CLIP, to 256. They reduced the precision in computing the image to text and text to image similarities and their losses from 32-bit floating point to 16-bit floating point. And so there's a substantial decrease between your maximum value when you use floating point 32 and when you use floating point 16, as well as the number of significant digits that you can have in decimal, 69 to 4. So this is one thing they use to improve the efficiency. Another thing is based on the intuition that each sample, whether it's image or text, can be represented by only a few tokens, a few select tokens. So they select 25% of the tokens with the highest token-wise maximum similarity score. And this is for both image to text and text to image similarities. So what does that look like? Well, for example, I'll take this image to text similarity matrix. Here for image 1, they take the top 25% of the text 1 through text n, and these are whole images and whole text. For your first image, or your second image, and so on. And so they take 25% of these. So then what's the effect of these? If you take only 25% of the tokens, right? So original, this is your baseline, this is CLIP. And our asterisk here denotes our final configuration that Philip uses. We can see a difference here. Embedding dimension is reduced to 256. Embedding precision, 16 point, and 25% of the tokens. So I want to draw attention to this training time here. When Philip uses 100% of the tokens, the training time is 2.31 seconds per iteration and reduces by a second approximately to 1.39 seconds per iteration. And we do see a slight drop in accuracy, but that's the trade-off that Philip has in order to have a much quicker training time. And so image to text retrieval, this is their fine-tuning experimental setup. It is a little bit larger. We have a 392 by 392 instead of 224 by 224. This is a better extract the features from the images. And fine-tuning is done on Flickr 30K and MS Coco with 30,000 text image pairs and 113,000 text image pairs, respectively. And I'll pass it to Anthony to talk about the results.
All right. Thank you, Kevin. Let's go over the results. Okay. So first, let's talk about the evaluation setting. 2 tasks are used to evaluate Philip, zero-shot image classification, and image text retrieval. This is done across many natural image data sets. These are images we would see out in the wild, like bald eagle, not synthetic ones or generated images. They pair these templates with each image. So right here we have this template and its respective indices. The caption is then put into tokens. And so the label for this image is bald eagle. We see at index 5 and 6. This is going to be relevant in a few slides. Here's another example of this bullock cart, majestic. So then Philip also presents their results on zero-shot classification, specifically with CLIP. This is across 12 downstream data sets, which are augmented with those templates I just referenced. And Philip claims that they outperform CLIP in top 1 accuracy. And we will see that they indeed do. They compare both models. Here we see a 5% increase on average. Here we see a 3%. And so I just want to point out, for some data sets, Philip does quite well, like double as well. And then for others, marginally worse. But overall, on average, FILIP does better. So domain-specific data sets are the bane of CLIP, and FILIP is presenting a solution for that or so they claim, with a 30% increase in performance, specifically on the FGVCA aircraft data set. They claim this is because they're matching patches with caption tokens, word tokens, rather than doing whole images with labels. So then let's look at the image text retrieval results. This is the second test they evaluated on. It's tested on these two data sets, Flickr 30K and MS Coco. FILIP claims they have roughly 3%, they're roughly 3% stronger than Align, and Align did better than CLIP on this task. And they make it a point to say that FILIP is trained with the least amount of data between CLIP and Align, with 340 million, while Align has 6 times more image text pairs with 1.8 billion. And so we see across the board that FILIP does quite well in bold here, doing great across zero shot as well down here. And it's marginally worse than Align for text to image on Flickr 30K, but we'll forgive them for that. So next we have some ablations that FILIP presents to us just to show us how they got their results. They claim that there are one improvement of almost 6%, and they claim that this is both in zero shot and fine-tuned settings. So if we look here, let's break it down row by row. So this is CLIP right here. We see CLIP's results. And then FILIP, they add some image augmentation. There's 1% increase to performance. That's okay. They add the back translation task, and that gives it a boost. That gives it like 4% increase across the board. Well, maybe not here, but yeah, mostly. And finally, there's the their bread and butter, the cross-modal late interaction mechanism. And this is what they're advertising, a 5% in performance across the board. And so they combine all these together, and they get roughly an 8% increase in performance on image text retrieval. And we see that's also that also occurs in zero shot settings over ImageNet. All right, then they give us some nice visualizations to for how we might potentially leverage it. So FILIP, they match image patches with caption text tokens that have the highest similarity. And they're going to show how they do that now in practice. So here's a raw image. We see some balloons. And the 5th index of the caption for this, they have all their templates they're using. But the label is balloon. And so we see that FILIP for the patches matches balloon for these patches. And we see for the most part, it's getting most of the balloons. Meanwhile, CLIP is not getting one. Of course, it wasn't trained to do this, but that's not the point. FILIP is mainly showing that it is capable of doing this. So it's not only capable of doing this for multiple objects in one image, but also we see that it's capable of doing it in lifeboats. It's capable of doing it in one object in an image. So this one's kind of interesting. We see the label is small white butterfly, which is index 5, 6, and 7 of the caption. And we see that for white, there's a lot of white on this butterfly, and then there's a butterfly right in the center. So it's doing a good job. CLIP, once again, is trying. And then finally, what FILIP shows is that it can get multiple components of one image. So in this example, the label is electric locomotive. We see the electric patches are these power lines here, and then we see the locomotive is the train up front. So these are some of the ways that patch image patch caption token training can be leveraged. So in conclusion, today we presented you FILIP, fine-grained vision language pre-training model. The main change between FILIP and CLIP and what makes FILIP shine is its use of token-wise similarity instead of image label Similarity. It is, for the most part, state of the art. When it was released, it was, and there's some later papers which build on it, such as Blip 2. And here are references. Thank you.
Okay, very nice. Excellent.